So, in our previous video, we had discovered the following model. We have A, as you can see here. We start by A, then we have an XOR choice. We go through either here or here. Then we have a parallel relationship here and here. And we rejoin from both sides here. And we finalize with D, of course. The question is, what happens if we have ABD as a trace from the real log system? Because if we look here, ABD, if we follow our model, is not possible. Let's start with A. So no problem. Here we have an XOR choice. So either we're gonna choose E or we're gonna choose this path. Here we know that we have a B. So we have a B. It means that we followed this choice. So if we have a B, it means that we need to have a C, because here you can see this is a parallel choice. And the C is absent in our real log, in our real system. This means that there is a discrepancy between our model, like here, the whole model, and what's really happening for our system. So here I drew one of the traces that the model could produce. So A, B, C, D, for example. And let's say we superpose our own real life trace on this possible trace from the model. So here we have A, that's normal. B, that's not a problem. Here we are skipping C, and here we have D. So the difference between our model and our real life log is 1, because here we have a discrepancy, an inconsistency. And that's the cost of our deviation. Here will be 1. If you look closely at ABCD here, we can see that it is the trace with the least cost that can be produced from our model that conforms to the real life log. So here the cost is 1. And there is an algorithm that searches through our model and finds this trace. And that's what the video is about. So before we get to the algorithm, I need to introduce new terms. Let's take AED. AED is a possible path in our model. As you can see, we can go here, we can look A, E, D. No problem. If you go down, let's create what we call an alignment table of ABD, which is the trace that we started with, A, B, D. Here we have seen already that we are skipping a step in ABD, and we try to superpose on it AED. So here, A synchronizes with A. This is what we call a sync move, or I'll just do it with a laser. So this goes to the top one, and it costs 0. So this is 0. This, for the B, I'll separate them this way. For the B, this is what we call a log move. Why a log move? Because the B is present in our log, in our trace, but it's not conform to the path that was presented to us with AED. So this AED is part of the path. It's coming from the model. So here, this is what we call a log move, and it will cost 1. That's cost 1. This is what we call a model move. Here, what's happening is that we have an E, and when we're trying to superpose it or align it with our trace, which is ABD, we can see that here we are skipping a step, and that's why it will cost 1 too. So that's a cost 1. Of course, the D here costs 0 because it's again a synchronous move. So we are lucky here because our model presents only 3 paths, which is ABCD. As we can see here, it only presents 3 paths: A, B, here C, then D, or A, C, B, D. That's the second path, and the third path, AED. So for a small model, it's not a problem. What happens if you have 1 million possible paths? That's what we need to focus on. So here I drew the two diagrams, the two Petri nets. This one represents our trace net. The way Petri nets work, I will do another video that explains precisely how Petri nets work. But what you need to understand is that this is what we call transition. You have in this one we have 3 transitions, and we have 4 places. These are what we call 4 places. The way a Petri net works is that you start with a token, so you would have a black point here at the starting point. This token would get consumed. This transition we would say would fire, and then you would find a token here, and step by step until we reach the end. So this trace net above represents the trace that we showed early on, and below is the Petri net that represents the model. Here I will show you. As you can see here, for example, we start by P0, no problem. We have A, no problem. When after P1, here we have to represent the XOR. So the way we represent it is that we create a silent T1 transition. This is not a transition that's present for us in the model. We don't have a T1 instance or event or whatever you want to call it. On the other hand, it's here. So we call it silent because we need to add it to represent the model in a Petri net. And here we would have, after we would start here, of course, A would fire, we would have a token here. So either E would fire and then the token here would get consumed. So we lose the token here. We would have a token here, or here we have a token and T1 would fire and then we would have 2 tokens here. So that's how we explain the XOR relationship here. So either here or here. After that, let's say T1 fires. Now we need to represent the parallel relationship. So let's start with here. And now we are forced, as we have these 2 tokens here in before B and C, we are forced to fire both B and C. This is what we call concurrency. We don't know who's gonna fire first, but both of them need to fire so that we can transition to have token here and here. And then we would go T2 would fire again. So here we'd have another fire, would fire again. As E didn't fire early on, so we don't have a token here, of course. We have our token that's coming from T2 coming down here. Then D fires and then the end. Let's see how our algorithm works. First of all, we start from here. So as you can see, ABD, we have the trace. The model starts at P0, meaning that it starts at place 0, and the cost is 0. No problem from here. We have 3 types of moves. So as you can see, we have a sync move, which costs 0, means we fire both together, meaning that we're gonna use our trace and we're gonna move in our model, and that costs 0. The log move, we fire trace only, meaning that we're gonna consume something from here, like from the trace, but not move anything from the model. And finally, the model move, which means fire model, only the model moves. And this is how our algorithm works. We start, first of all, as we said from here. First move is sync A. Why sync A? We have ABD. As you can see, ABD. We're gonna we're gonna consume the A. We're still gonna have the BD, of course. And here, we're gonna fire the transition A. And we're gonna have a token here. The token from here is consumed, and we're gonna have a token here. No problem here, cost is 0. Now, we have a choice. So either we will go this path, or we will go this path. Meaning that if we go to our model, we had the token here, right? So either we're gonna go this or this way. Let's ignore this path. Let's ignore it for a moment. Let's follow this path for this instance. As we can see here, the model move, if we do model move, it costs us 0 if it's silent. Here it says silent 0, meaning that when I here trigger T1, fire T1, it costs me 0. So here when we fire T1 and we go from having a token here and token here, it costs us 0. So we fire, first of all, we decided to follow this path, of course, and we have 2 tokens here, and it costs us 0. After that, as I have in my trace BD, I'm gonna search for B first, right? So B is gonna fire. I'm gonna have, and that's a sync move because, as you can see, we have BD in our trace. The log is gonna consume the B, and here in the model, we're gonna fire the path of B. And we're gonna find ourselves with the token here and the token here. As you can see, the model here, the model says P3 plus P4 means we have tokens in place 3 and place 4, and the cost is still 0. And we still have D in our trace log. Now, next step, we're gonna have to do a move just on C. But the problem is that we only have D in our trace. We already consumed A and B, but we only have D. So this is gonna be what we call a model move. And C is not C here is not a silent transition, of course. So this is gonna cost us 1. We are forced to do the transition of C, but because otherwise T2 will not be able to fire, and T2 needs a token here and a token here. So we're gonna be forced to do a model move, and that's gonna cost us 1. After that, we're gonna fire T2, of course, because we did these 2 tokens fired, and when T2 fires, P6 is filled with a token. So that's where we find ourselves. Here we say, first of all, model move C1, and that costs us 1. T2 fires, and that costs us 0. Then we have D that fires, and we already had D in our trace. So here it costs us 0, because that's a sync move. And we are done. We are done because we reached here 0. Our trace log is empty. Model says P0, and the cost of this path is 1. Until now, everything is clear. Now, if we follow the other path, early on, if you remember, we said we're gonna ignore this path. Now we're gonna consider it. So we go back here. We had the token at P1. We fire E1. We don't have the issue now. In our trace, we said we had ABD, right? We started with ABD. A is consumed. Here, A is consumed. We still have B, D. We don't have an E. So E is on its own a modal move, because here, as you can see, it's a modal move, meaning that it will cost us 1, because we don't have in our model a path to get a B. And the path, we already considered it, which had a B. So that's a modal move. And that's gonna cost us 1. Here, as you can see, cost us 1. We find ourselves at BD from our trace. Model has a token in P6 and costs us 1. From this position, what happens? We don't have a choice. We need to finish what we started. We need to find a way to take B from our trace, because we have a token here. We don't have a way to consume B in any other way. So log move will cost us 1. We are forced to do it. So, and this is log B1, and that costs 1. After that, we still have D. So when we are here, we have D, and we have a token here. D needs to fire, and then that's a sync move, because we have D left in our trace, D in the model. They both fire, they are both consumed, and we have a token here in the end place. And this path's total cost is 2, because here that incurred 1, and here it incurred 1. This is 2, this is 1. This wins. As you can see, the name of our algorithm actually reveals it. It's A star search, cheapest path from start to goal. So we found the cheapest path. This is a win. Now, let's go down. You can see it for yourself. This is the path. So now if you were coding and you're using PM4Py, you'd use only this one line to do all of what we did. And this would be the result. Alignment A, B, C, and the cost is 1. That's the winner that we discussed. Fitness is 0.75, and it visited 6 states. The 6 states are here, so these are 6 states. So as you can see here, 1, 2, 3, 4, 5, 6. Now back, the function conformance diagnostics alignment takes 4 inputs. So log, the event log, the collection of traces, the traces from the real system, and it's a pandas data frame. After that, it's a model net. So our model net, this basically, it's a Petri net. It's a Petri net object. Internally, it's just 3 sets: places, transitions, arcs connecting them. So basically, our places here, our arcs, that the transitions, and the arcs connecting them. So that is clear. Then the initial marking P0 of your model net, where the token starts. A marking object, a dictionary mapping places to token counts. For your model P0, P01. So it's like a dictionary. This is something you would know if you're using Python. Each key has certain value. The same thing goes for the FM here, which is the final marking. And that was our video. If you liked my input, the video, please subscribe and comment. Tell me what you want to see in the next video.